Hey there, welcome to the Energy Blueprint Podcast. I'm your host, Ari Whitten, and today I have with me Dr. Laszlo Boros, who is a professor of pediatrics at UCLA and the co-director of the Stable Isotope Research Laboratory at the Los Angeles Biomedical Research Institute, with a primary focus on studying cancer cell metabolism. He was born and educated in Hungary, and his medical background includes 3 years of gastroenterology and pancreatology, focusing on chronic pancreatitis and pancreatic cancer. He's an internationally proclaimed expert of metabolic water biochemistry, as well as deuterium-mediated kinetic isotopic effects and health and disease. So I'm sure that many people listening to that are probably like, what the heck did he just say? And I promise you, we're going to do a good job of simplifying what this is all about. I want to just say at the beginning of this, the primary focus here is something called deuterium, and we're going to talk a lot about this compound in the body called deuterium and how it accumulates in water in our cells, and how we can deplete it, and what it does when it accumulates, the harms that it can do when it accumulates in our cells. And one of those is cancer, which is why Dr. Boros has such an interest in cancer, or I should say maybe why he has such an interest in deuterium from the background in cancer research. And there's also some research linking this compound, deuterium, this accumulation of it, to a range of other health problems. And there's research currently being conducted in relationship to chronic fatigue specifically. So we're going to be talking all about deuterium, and it is a complex topic, but I'm going to do my best to ask simple questions and simplify, and I'm sure Dr. Boros is going to keep that in mind as well, and do his best to make everything as simple and easy to understand as possible. So welcome to the show, Dr. Boros. Such a pleasure to have you.
Great. Thank you very much. It's an honor to be part of the show.
Yeah, thank you. So first of all, I would love for you to tell a little bit about your background of how you became interested in deuterium. And I was watching one of your presentations earlier today, and you were telling the story of kind of this dinner party in Hungary where this guy approached you and started talking to you about this deuterium depleted water, and how amazing it was. So can you kind of talk about how you became interested in the first place? And then I also want to just talk about what deuterium is.
Yeah, so by training, I'm a medical doctor, but I do research and I teach biochemistry, medicinal biochemistry. And indeed, in Los Angeles, we had a dinner with Hungarian friends, where one of the participants approached me, who was actually involved in freight or shipping, with this water, which was deuterium depleted water, and he was telling me how wonderful it is. I was like anybody else, I was a skeptic at first. So I just told him, listen, if that's just the scenario, just drink as much as you can. Yet I was not really after this until actually I got a contract with the guy who makes this water in Hungary. His name is Dr. Gábor Somlyai, and he was studying this water for quite a long time. He's a biologist by training, and I did not know much about this water until he was pursuing studies through UCLA. I actually run metabolic profiling laboratory services at UCLA, so my job is practically to look at compounds and look at their biochemical or metabolic effects. And if there is an effect, then we have a certain type of tracer technology, which is very sensitive in studying metabolism. And if there's an effect, then we interpret it from the medicinal or from the basic science point of view. Now, interestingly and surprisingly, this water, after they paid the full price for running a complete UCLA-based basic science studies, this water had a dose-dependent effect on certain biochemical platforms in the cells, including mitochondrial energy production, mitochondrial substrate oxidation, based on the deuterium content of the water. Now, deuterium is a heavy isotope of hydrogen. Hydrogen comes in three forms or three flavors. Two of them are stable isotopes, meaning that they do not radiate any bad stuff. Those are hydrogen and deuterium. Deuterium has one extra neutron next to the proton. We know hydrogen has a proton and deuterium has a proton and a neutron, so it makes it twice as heavy. It's like a very heavy twin brother, twice the weight, and obviously
a twin. Just to clarify, a twin brother of normal water or normal hydrogen.
Hydrogen, and when it gets attached to oxygen, then it makes heavy water. So heavy hydrogen exists in nature, attached to various other atoms, carbon or nitrogen or oxygen most often. And actually, hydrogen and deuterium, those are called elements, those are atoms. And because they only have protons and electrons and neutrons, hydrogen is the first and the smallest and the fastest and the most active element in nature. It's actually the first atom in the periodic table. So it only has one proton. There's no more simple scenario or atomic particle than hydrogen. And when you attach a nitrogen to it, it actually makes it twice as heavy. So in nature, the largest isotope effect is between hydrogen and deuterium. There's no other atom that has this doubling of mass effect. Every other isotope has a fraction of the fraction of increasing mass. So this doubling of weight or doubling of mass is really a big burden on any biological process that transfers or moves this hydrogen, and deuterium makes this transfer process very difficult to carry out by cells. And just to going back to your original question, when it comes to heavy water, which my friend was talking about it, this heavy water depleted from drinking water, meaning that the water is more light. Deuterium depleted water means that the hydrogen pool of water has less deuterium. In nature, there is about 155 deuterium for every million hydrogens. That's 155 ppm. That's the water in the Pacific Ocean. That's the largest water pool and the highest, most abundant deuterium source. And everything that is fractionated, evaporated, removed by any physical method from the oceanic water, for example, by vapor, by formation of clouds, will have less deuterium, and that's what we call deuterium depletion, when the extra fraction or the new fraction of water has less deuterium, and this is what we call in nature deuterium depletion. Interestingly, when you have clouds that fly over or kind of spread over lands and yield rain, those have less deuterium because of this evaporation process. Gets rid of deuterium somewhat because deuterium is heavier, so it has different physical chemical characteristics. It makes water more viscous. It makes water more heavy, and it changes its freezing and thawing and melting temperatures, and that's why practically physics and physical processes constantly deplete deuterium or constantly change the hydrogen deuterium ratio in water and also in molecules that are actually synthesized from water. And all molecules, all organic molecules are synthesized from water because photosynthesis breaks water with the energy of light, and it's also a deuterium discrimination process. So after I talked to my friend, after we finished the study, we have learned through our experimental design that actually deuterium depleted water has a large effect on energy production, especially in mitochondria, which is dose dependent, and the effect is linear, meaning that the change of dose causes the same amount of change in energy production. So we figured there's a very basic biochemical constraint type of in a relationship between deuterium content of water and energy production of cells.
Okay, so let me jump in here for a moment. I want to make sure that we don't lose people who don't have any familiarity with some of this stuff and maybe never took
Sure.
college or high school chemistry. So first of all, just water is H2O, two hydrogens and an oxygen. We have lots of water in our bodies, in our cells, in our mitochondria, obviously. Deuterium is it D2O? Is one normal hydrogen and one deuterium in place of that normal hydrogen that's attached to the oxygen? So what is heavy water or deuterium-rich water?
So there's light water, there are semi-heavy water, and there's heavy water. And you're right, light water is H2O, semi-heavy water is DHO, and heavy water is D2O. So
Okay.
in other words, if you don't have any hydrogen replaced by deuterium, that's light water. If you have one hydrogen replaced by deuterium, that's semi-heavy water.
Okay.
If you have two deuterium replacing hydrogens, that's heavy water.
Okay. So just to correct a common misunderstanding that so many people have, we all think of, water is H2O. Our bodies, we drink H2O, our bodies, our cells are filled with H2O. That's actually not true. Our cells are filled mostly with H2O, but with some DHO and some D2O in there as well.
Yeah.
And basically, the gist of this whole concept is that more of this DHO or D2O, more of this deuterium accumulated in our cells is linked with various kinds of harm. Correct?
Diseases including, it deprives energy metabolism, energy production, and as a consequence of that, you're right, it harms the cell.
Okay. So but I want to get into some of the mechanisms of how it causes harm. But first, I'm curious, does deuterium play any positive role in the body? Is there any, any beneficial reason that any beneficial purpose it's serving? Or is it the case that just the less deuterium we have in our bodies, if we could deplete it all the way down to 0 parts per million, that would just provide progressively more benefits? Is there any kind of middle ground where we want to have sort of an optimal range, or it's just less is better?
Well, different molecules, different biomolecules have different amounts of deuterium. We believe that the biological range or the biologically relevant range is somewhere between 95 to 120 ppm, and most deuterium accumulates in DNA or nucleic acids simply because they have hydrogen bonds, and because hydrogen is so active and structure is so active, that actually binds the two helices of the two sugar skeletons of the two helices of DNA. There's actually deuterium in DNA, and actually that makes DNA to grow. Bacterial DNA depends on deuterium to grow constantly, and this is actually yeast and bacteria growth requirement to actually collect retained deuterium. So based on phenotype, based on cell type, deuterium has a biological role to control cell proliferation or cell growth. So cells or prokaryote cells who actually specialize on continuous growth and fermentation of substrates, they collect retained deuterium, and that's their purpose practically. So deuterium has a role in biology. Certain phenotypes or certain type of cells like to accumulate deuterium for their constant growth. It's more like a competitive biological behavior, but it's not very compatible with eukaryote or mammalian cells, which do not divide on a constant basis unless they become cancerous. And those cells actually limit their own deuterium by these organelles, mitochondria, which are able to deplete deuterium for the cell. And this deuterium depleted water can actually produce certain, DNA with limited number of deuteriums. And those DNA size, the size of DNA in cells that can limit or control deuterium, can be contained in a nucleus. So practically the difference between a bacteria and a liver cell, for example, is that the liver cell is able to deplete deuterium, so it actually can wrap up its DNA and pack it into a nucleus, and it can sit there for a certain period of time, and it only transcribes genes for normal cell function. Prokaryotes or bacteria cannot do this simply because they don't have the tools to deplete deuterium. They don't have mitochondria. In fact, they retain deuterium for constant growth. It's a very competitive and a very efficient way of surviving in nature, yet it is a very, metabolically, it's a very harmful way of living in a organized or in a host organism where actually continuous cell proliferation is really not a desired pattern.
Gotcha. So let's jump, I think, to mitochondria first, and the sort of the primary mechanism of how this deuterium is causing harm. I know there's a few, probably several nuances here, as far as you mentioned there, that mitochondria are built with the capacity to deplete deuterium, but there's also this element of how deuterium can damage mitochondria. So what's the mechanism there of how this accumulation of deuterium at higher levels causes harm to our cells and to our mitochondria?
Yeah, so what we need to know about mitochondria is actually uses these very delicate proteins, we call them nanomotors, and literally they are actually nanomotors that spin in the inner membrane of mitochondria. Has two membranes. There's an outer membrane and there's an inner membrane, and between these two membranes there's a space, we call it inner membrane space. And what mitochondria do is it takes in nutrients, mostly in the form of oxaloacetate or acetyl coenzyme A, but actually it's an organic molecule. And actually mitochondria would harvest the hydrogen from these organic molecules, and CO2, carbon dioxide, is the product of this proton or hydrogen harvestation process. And this hydrogen is actually pushed in and between of those two membranes. And when they return into the mitochondria, they rotate these nanomotors. And by rotating these nanomotors by an electromagnetic force, they actually get transferred to the membrane using these nanomotors. And in the meantime, ATP or adenosine triphosphate is produced, which is our energy currency in our cells. But these nanomotors are very sensitive to the effect of deuterium, meaning that it's a highly it's a very fast, rapidly rotating protein. You can imagine at maximum velocity, they rotate at 9,000 rotations per minute. So these are actually Formula One race car engines or rotating parts. So if you throw a particle that is twice as heavy as it's more like a sand in an engine, it actually unbalances it. There's a unbalancing effect of deuterium, so they can actually physically break these nanomotors, besides other harms that they can deliver. They alter the structure of proteins. Proteins don't fit anymore. Proteins are not able to smoothly change their conformations. As you mentioned in the beginning, it's a very complicated picture, but what we need to focus on is practically how deuterium damages the physiological structure of mitochondria, including the rotating parts and also the structural parts, which actually keep these elements in place, more like the building blocks or the structures. And as a result of that, mitochondria need to work with as little deuterium as possible, meaning that our food, our contaminated water from the environment has to be depleted of deuterium before they get into the mitochondria, just to make sure they don't cause any harm.
So what actually is what is the element that's causing harm here? So is it that the deuterium atom itself is larger than a normal hydrogen atom, and so when it's pushed through this nanomotor that's
right.
pumping, the ATPase pump on the mitochondria, when it's being pushed through that pipe, it's like, is it literally just too big, such that it's kind of plugging or scraping up the pipe?
Yeah, it's you can imagine a football game which you just actually throw in a medicine ball instead of a football. So it's twice as heavy, it's twice as big, and it's really not compatible with this dynamics of the game itself. So you can imagine if you just change the ball of a football game twice as heavy, twice as large, the whole game will stop, because actually it's not designed. Those players would not know what to do with it. So that's how surprising, that's how shocking it is for mitochondria when a deuterium gets in there. It just actually changes the whole game. It's just actually because of its weight, it just breaks things. It's like a ball in a China store practically. It is too heavy, too large to fit in proteins and actually to participate in any rotating movements, and that's why it's actually very harmful for mitochondria because of its physical properties.
Now, so I want to dig into this a little bit more, because let's say someone has very low deuterium levels versus very high deuterium. So let's say someone's got, I don't know, 100 parts per million in their cell water. And we can talk later about, the ways to measure this. I know there's some methods of actually assessing how much deuterium is in your body. But so let's say someone's got 100 parts per million deuterium versus 150 parts per million or 160. Either way, there's still quite a bit of deuterium in there, or there's still some deuterium in there that the mitochondria are having to deal with. Now, obviously, they have to deal with more in the scenario where there's 150 or 160 compared to 100. But either way, there's still some deuterium that's passing through those ATPase pumps. What is actually the difference in terms of the damage being done to mitochondria if you're at 100 parts per million versus 150?
Yeah, so here's the catch. Usually mitochondria should not have any deuterium, because whatever is in the environment, your biochemistry is pretty much like a chemical protective fence around the mitochondria. And nobody disputes that biophysics is important in understanding the damage delivered by deuterium in the mitochondria. It's actually biochemistry that protects the mitochondria, so neither 155 nor 100 ppm can get close to the mitochondria at that level as far as deuterium count. Deuterium should not reach mitochondria from the environment, and this is why our body has so many filtering layers and so many biochemical mechanisms to actually get rid of deuterium before it would get into the mitochondria.
Okay, so let me just interject here real quick. So basically what you're saying is some body tissues may have, let's say, 150 or 120 or 100 parts per million of deuterium, but at the mitochondrial level, we should have water that's inside of the mitochondria that is completely purified of deuterium and has no deuterium. However, in some scenarios, which I would love to talk about next as far as why that happens, but in some scenarios, for whatever reasons of dysfunction, the mitochondria starts to get deuterium inside of there. Is that accurate?
That's right. That's right. So mitochondria produces its own water, which I didn't mention. When protons get into the matrix or into the inner mitochondrial space, oxygen is waiting and water is produced. Because oxygen is reduced by hydrogen, or oxygen is bound to hydrogen, two hydrogens, and actually metabolic water is what is in mitochondria, and that water is produced from food. It's not from the water from outside. Mitochondria produce its own water. We call it matrix water or metabolic water, and the hydrogens come from food, from organic molecules that we oxidize, we burn in the mitochondria. It's, for example, like your car engine. You have to use fuel to be burned, and actually water is produced in your engine, but the oxygen comes from air. So practically it's the same scenario. You're burning an organic material, and you have to look at your food, what's the deuterium content in your food, to determine what's the deuterium content in your mitochondria. So if your food has 100 ppm, through glycolysis, through fatty acid synthesis, through various interchange reactions, your cells, your body is trying to get rid of deuterium from food or from food components. So by the time they get to the mitochondria, they don't have deuterium. And practically this is how you protect your mitochondria. You actually use a lot of biochemical reactions and change hydrogens or deuterium to hydrogen from cellular water, which is also coming from mitochondria. So practically your inner water production system is protecting your deuterium-depleted water production system, or inner water protects your substrates, your food items or food components. By the time they get down to the mitochondria, they don't contain any deuterium either.
Okay.
So practically the environment and the load of your food of deuterium will determine how much of this deuterium will get down eventually to mitochondria. And if there is a damage delivered, it's occurring through food. It's not occurring through water necessarily.
So what is the, I want to say rate limiting step, but that's not quite the right word in this context. But where are these major checkpoints that are kind of preventing this deuterium from getting into the mitochondria? And which one is, or sort of the key one, if there is such a thing, the key one where most of the dysfunction occurs, where that allows this deuterium to start leaking into mitochondria?
It's a process called glycolysis. Glycolysis is how you break down glucose. And the third step of glycolysis is an isomerase reaction. It's called hexose phosphate isomerase. I don't want to scare people away. That's why I was not mentioning biochemical reactions by name, but we have to, after all, to understand this.
This is part of the Krebs cycle, or the citric acid cycle.
It's not the Krebs cycle yet. It's actually glycolysis. Glycolysis has three particular steps that actually depletes deuterium very rapidly from glucose. One is this hexose phosphate isomerase, which specifically turns glucose 6-phosphate into fructose 6-phosphate. The second reaction is called triose phosphate isomerase, which actually turns glyceraldehyde 3-phosphate into phosphoglycerate. And the third one is called enolase. Enolase takes out a whole water molecule from glucose simply because oxygen and 2 hydrogens are leaving glucose, simply because they want to get, glycolysis has 10 steps practically to check on every hydrogen on glucose to make sure it's not deuterium. So before glucose gets into the mitochondria, it has to go through glycolysis. It has to break down from a 6-carbon metabolite into two 3-carbon products. We call them pyruvic acid or pyruvate. And this pyruvate is the source of mitochondrial substrate oxidation. But by the time glucose turns into pyruvic acid, it should not have any deuterium unless there's too much deuterium in the environment. So this depletion process is not complete, not very efficient. And if that happens, which we know unfortunately now because of the environmental and because we eat a lot of sugar, or actually ketogenic diets, fat don't have deuterium. So in nature, nature makes sure that the fat or the ketogenic substrates don't have deuterium, and that's simply because in nature, fat can only produce from mitochondrial metabolites, specifically from citric acid. So every fat source in nature is from mitochondrial source, so it's deuterium depleted. So comparing sugar ketogenic diet with glucogenic diet with glucose or carbohydrate diets, the main difference is their deuterium content. And if glucose is too extensively entering mitochondria, or glycolysis is not efficient because there's environmental deuterium exposure that is higher than expected for glycolysis to work, then there's a chance, there's a possibility that eventually deuterium can get into the mitochondria. It's not desired though, but we believe that nutritional and dietary recommendations that involve too much carbohydrates can eventually damage mitochondria simply because of the substrate that enters mitochondria have higher deuterium content than mitochondria can handle. Okay. So glycolysis, membrane transport of glucose, glycolysis several times. If you eat a glucose molecule, it goes through glycolysis in red blood cells, then it goes through glycolysis in liver cells, and it goes to glycolysis in target cells. So actually, it's not only one time, but it's actually at least 3-4 times of glycolysis before any substrate gets into the mitochondria. So our body at different tissues, at different tissue levels, have the glycolysis just ready to deplete deuterium as much as possible. So these steps are repeated in every cell. And after all, they are so intense and so rapid. So by the time your substrate get to the target cell mitochondria, they should not have deuterium. And practically, this is what biochemistry is about, how to deplete deuterium from organic molecules.
Gotcha. Okay, so there's a few nuances I want to dig into here. First layer is, and I think these are pretty quick answers, but the first layer is when these glucose molecules are going through glycolysis outside of the mitochondria, in these multiple steps, you said red blood cells, liver, and then the target cell, they're being stripped of deuterium. And then where is that deuterium going? How is it leaving the body?
Deuterium gets into the water. So the reaction works that actually dropping a deuterium from glucose and getting a hydrogen from water. So that's how it gets exchanged, and the deuterium that was dropped gets attached to the water. Water gets out of the cell and becomes urine after all.
Urine, or also exhaled as well?
Urine or exhaled, or actually it becomes poop, or become part of feces, because we just learned very recently that our cells are able to ship lactate out to the gut, where actually these bacteria, the prokaryotes, are waiting to collect deuterium from lactic acid, and actually what they return is a short chain fatty acid. It's called propionic acid. So what we are describing here is a bunch of biochemical, set of biochemical reactions and collaboration between different type of cells and even bacteria of the gut, simply just to get rid of deuterium as much as possible.
So that may be another mechanism by which a dysfunctional gut microbiome contributes to poor health by preventing adequate depletion of deuterium.
Right on. You're correct. That's right.
Okay. So the next layer of the story, I'm trying to remember what I wanted to ask. I've heard some people say, and I think maybe even you say this, that mitochondria are depleting deuterium. So, but it sounds like in what you just described that it's not necessarily the mitochondria, it's more the steps before the glucose molecules or some of these other molecules are arriving at the mitochondria. It's the steps before they get there that are depleting the deuterium. Which one is it?
Yeah, but mitochondria also retained this mechanism or the ability to deplete deuterium in case there's too much deuterium in the environment. So the previous or the preceding mechanisms or the reactions are not able to get rid of them all. If there's too much environmental deuterium load, the glucose is above the natural enrichment, which unfortunately is the case in GMO foods, then your mitochondria has to have its own mechanisms to actually get rid of deuterium. And the way mitochondria do this is that when it's called the urea cycle, you probably heard about the urea cycle, which takes place in the mitochondria. It actually takes heavy water out of the mitochondria, and urea is produced. So mitochondria has these FO elements next to the nanomotors. So the nanomotor does not get deuterium, but actually deuterium is getting collected into this protein sacs, the sac that is actually on the side of these nanomotors. And there are gating mechanisms. There are actually filters of protons that enter the nanomotors. And if the proton is too big, in that case it's deuterium, it's actually sent to the other way, to this FO subunit, which collects deuterium. And when it gets too heavy, then this sac will be disassembled from the nanomotor and it will be replaced. So, and you're right, mitochondria has its own ability to deplete deuterium or filter out deuterium. That's practically kind of the last resort of the cell to protect their mitochondria, the mitochondria's own defense system. Yet, they have to maintain this simply because sometimes the environmental deuterium load is so high that the precursor mechanisms, the predecessor mechanism that protect the mitochondria are not sufficient. Mitochondria has to take care of its own, or of their own, and the urea cycle and these deuterium collecting proteins in mitochondria can actually accomplish this task.
Okay. And then if somehow all of these mechanisms are being overloaded constantly, then you still accumulate too much deuterium in the mitochondria where they start to damage these nanomotors. Is that correct?
Then nanomotors break and mitochondria die, and you set up a whole set of diseases, yes.
Okay. Including cancer.
Including cancer, diabetes, obesity. These are cellular metabolic diseases because of the broken nanomotors. Once the nanomotors break, then the biological oxidation process slows down. There's metabolic or molecular crowding. Cells are not able to get rid of glucose or fatty acids. The fatty acids start accumulating, especially if they are loaded with deuterium. And as a result of that, there's this metabolite crowding. And this, because of this crowding, there's a whole host of neurodegenerative or cellular degenerative diseases, which actually will end up in the form of cancer, diabetes, obesity, autoimmune diseases, you name it. Practically, I believe that besides breaking bones, all chronic diseases related to some kind of a tissue-specific deuterium overload, and they can be actually improved by depleting deuterium one way or another. We'll probably going to cover those aspects of it, but practically it's a deuterium disbalance when we talk about diseases, and the primary mechanism is practically too much deuterium breaking too many nanomotors and too many mitochondria dying.
Okay. Well, I don't want to gloss over what you just said because I think that's a very big claim, and I want to emphasize it. So you believe that this deuterium story is central, is a big contributing causal factor to a huge array of diseases. Is that accurate?
On a tissue-specific manner, certainly.
Okay.
And I'm saying this as a medicinal biochemist. It's not a medical opinion. It's a medicinal biochemistry scenario. So we are explaining, we are actually exploring mechanisms. We are not suggesting as a disease or even a treatment scenario. It's practically an underlying mechanism behind a tissue-specific mechanism behind disease. How to treat this, how to get rid of it, how to solve this problem, that's a whole different matter. We are talking about mechanisms, and obviously there's many different, there's dietary, there's lifestyle, there's pharmaceutical, there's many approaches, which is not part of this discussion. We are actually looking at very basic biochemical medicine or biochemical mechanism to explain disease itself.
Okay. But so you do believe it is a big factor in many diseases?
It's a big factor in many diseases. That's right.
Okay. I want to come back to one layer of the story that you were just explaining. So we have all these sort of checks and balances and steps of depleting deuterium before these molecules ever arrive in the mitochondria. So you've mentioned that a big factor is obviously the load of deuterium in the diet and the environment, but is it also the case that these internal checks and balances and systems to deplete deuterium, the glycolysis, as well as the mitochondria, that those parts also become dysfunctional in a certain way? Like, let me ask this a different way. Would it be the case that somebody who is young and healthy and physically fit and eats a very good diet, irrespective of the deuterium content, but just somebody who's very fit and young, would they have a greater capacity to deplete deuterium at all those steps than somebody who's older and, obese and sedentary and unhealthy?
That's right. That's what we believe. Aging, which you are talking about, is practically a deuterium-related process, and actually the cleaning or filtering out deuterium, it actually gets less efficient by aging, and it's practically just because these mechanisms, these proteins, they replaceable mechanisms, they are actually wearing out. I'll give you an example. Your car filters out gasoline at 3 different places. The gasoline filter at the tank, the gasoline filter at the carburetor, and the gasoline filter at the entrance of the gasoline mixture with air filter and the gasoline filter. They just filter constantly. Now, any of those filters get clogged up over time, it will load deuterium to the next filter layer. So practically your systems fail over time to get rid of deuterium completely, and this is pretty much the same in the human body. When glycolysis is less able to handle flux, meaning that your glycolysis is not as intense, in that case scenario, you actually have more deuterium to get into the mitochondria. The mitochondria has its own filtering system, but if it's overloaded over time, then mitochondria start dying. So practically this filter system, as they are lined up to each other, they fail in the same sequence practically. And aging, we believe, is dependent on oxygen delivery, depending on breathing functions, depending on heart rate, and eventually metabolic water production. And this metabolic water production is very important, very crucial, and it's necessary to get rid of deuterium very efficiently. So it's not necessarily just deuterium filtering, but all the mechanisms and all the linked biochemical reactions that actually get rid of deuterium. So filtering is one thing, but getting rid of it, it's another. If your oil filter is clogged up, if your air filter is clogged up, if your gasoline filter is clogged up, then you have no ways of filtering out or getting rid of deuterium. So practically all these mechanisms have to be in place, and over time, they actually exhaust one another. Practically, you have to deal with this scenario over a longer period of time when you age. And you're right, these systems, when they actually fail one another, then aging and diseases may occur. Yet disease is not as important as natural aging. I believe in a low deuterium environment, but over time, as every moving part get worn out, nanomotors get worn out, the replacement is not as rapid, the removal of deuterium is not, even the filtering is effective, the removal is not as efficient, you have less urine, you have less hormonal regulation. So all these mechanisms play in the same direction, is filtering out and getting rid of deuterium. Any part of this process is somewhat diminished or compromised, then you might have a problem of deuterium accumulation, and it's just the different ways of how and what's the underlying mechanism that contributes to deuterium accumulation the most. But usually it's the complementary systems together that eventually fail, and that's what we know. It's a close to terminal situation. When somebody has too much deuterium, then there's no way to get rid of it through breathing or through saliva or through urine or feces. In that case, you actually end up with extra excess deuterium, which has devastating effect on cellular functions.
Gotcha. This is fascinating stuff. So I have my mind's like overflowing with questions here, but one layer just to segue from what you're just talking about there is where my mind is going is mitochondrial capacity. So let's say, I know you said there's a whole bunch of steps before the deuterium ever arrives at the mitochondria, but let's just say the capacity of mitochondria to deplete deuterium is very important. We know, so is it just aging, or is it also a person's lifestyle habits that contribute to their mitochondrial capacity? So I'll give you an example. Like, we know from studies looking, at muscle biopsies and assessing mitochondrial capacity that from the ages of 40 to 70, most people lose about half of their mitochondrial capacity. But when you look at studies of specifically 70-year-olds who have been exercisers for their entire life, they don't lose half of their mitochondrial capacity, and they have mitochondrial capacity similar to 40-year-olds. So I'm just wondering, that seems like it would be a big factor to me in retaining the capacity to deplete deuterium. And I'm also thinking that probably, exercise also stimulates these glycolytic pathways. So I'm wondering if that system can be sort of exercised and built up to a higher capacity through physical exercise as well.
That's right. And exercise actually makes the gut, the microbiome, more involved in deuterium depletion because you produce more lactate, and lactate gets shipped to the microbiome, and then you get a ketone body back for oxidation. These individuals may not live much longer, even though they have retained some mitochondrial mass, simply because they might not be able to get rid of deuterium, even though they can filter out. After all, they might not be able to get rid of it as efficiently. So it's only a guarantee of longer, more quality life if all these mechanisms stay in place. And you're right, number of mitochondria can be induced or can be actually maintained at high levels. And these individuals have better quality of life, let's say. It's not necessarily a longer lifespan. It may be somewhat longer than the average population, but practically when it comes to getting rid of deuterium, that's the key, after all, to understanding aging or the time of death. They die of different causes, because once you compromise circulation, once you compromise heart muscle function, once you compromise joint functions, meaning that you have more inflammation in your joints. Let's say you load your physical exercise. By physical exercise, you actually wear out your muscle mitochondria or muscle cell mitochondria more than, let's say, your skin or your gut cell mitochondria. If you load certain cell systems or certain organs, for example, circulatory organs or lungs and hearts, even though you are accustomed to a higher exercise level and you have higher mitochondria numbers in your cells, their function is not necessarily filtering deuterium. Their function is producing more ATP in a low deuterium environment. Once your glycolysis or once your additional mechanisms are not as efficient, unfortunately, even though you have more mitochondria, they might not work as efficiently as you believe, or they might not be able to deliver as much ATP as you believe, as you hope for. So after all, exercise is very important to make sure that you have a quality of life and you actually carry on with better health. And no question, exercise is very important, especially with good nutrition. Good nutrition is, in my view, in my terms, is actually a natural ketogenic type of eating. So less carbohydrates and less proteins. Usually these people who exercise more, they actually eat more protein-rich diets, which may not be as favorable as far as mitochondrial health go. You can induce mitochondrial number in muscle cells, definitely, but based on how you feed these mitochondria, it's because of the mitochondrial high turnover, because there's so many mitochondria actually perishing and this mitochondria rebuilt at higher rates. These may be all demanding on tissues, depending on what kind of source, what food source you eat, what's the deuterium level. So all these complex scenarios come down to one very important question, is that practically how you can maintain strength and how you can maintain ATP synthesis at a higher rate based on your exercise pattern, how you can involve your gut bacteria, how you understand this very complex system, after all, to beat it, and how to get rid of deuterium in a constant level. And if you actually do it in a smart way, meaning that you know how to protect those mitochondria, not only produce them, but how to protect them, and that's practically to a ketogenic low deuterium diet, then you have a very good chance of living a very good, healthy life with a good exercise pattern, and you can enjoy it for a better health, definitely.
Okay. So just to be clear, you don't think exercise necessarily bolsters the systems to deplete deuterium that well?
It is necessary, but it's a moderate exercise. You know, the exhaustive type, the exercise is really another kind of, it's another strain on your system. The overdone type of exercise pattern is not necessarily healthy, but the regular exercise, the moderate exercise, the constant exercise is actually very good, simply because it does not exhaust an energy producing system, but actually it ups it to a higher demand. So exercise again has different levels and different scales. And in that way, you have to find the one that is actually serving your heart the best. And for some reason, the exercise pattern or type of exercise that you deliver, you can be a biker, you can be a runner, you can be a weightlifter, you can be a bodybuilder, you can be a swimmer. There's many different ways of exercising. I think the best way to exercise is practically find a moderate to demanding level that is not very exhaustive of your cellular systems, but maintain these high energy producing mitochondria in good shape. And if that's the scenario, if that's the case, then you have a good chance to live a very healthy and a very productive and a very joyful life.
Okay. And I know you alluded to this a minute ago, but you're saying avoid exhaustive exercise for what reason? You're worried about it damaging what?
Yeah, it's practically high velocity. It's a high demand on your energy producing system, your mitochondria. After all, mitochondria can be rebuilt, and you see high number of mitochondria, but it may be also a high turnover. Turnover, we mean that it's a new synthesis based on the death rate of mitochondria. That's the turnover. So exercise, for example, when you look at competitive sports, you can only do it for a certain period of time of your life simply because it would actually damage physically and also metabolically your organs, meaning that if you're a bodybuilder or if you're a long distance runner, you have to do it in a moderate fashion in between competitions, meaning that you have to keep yourself in a good shape, yet you don't have to run a marathon every day. If you know what I mean. Practically, you have to prepare for those challenges, but you don't have to overload your system. You don't have to exhaust your system on a regular basis because that may not serve the purpose of staying in good health. Yet,
Gotcha.
challenge is very important. Exercise is very important, but you have to adjust to the kind of optimum level that your body can handle, and just be kind of careful how much you load and how constantly you load your body, simply because your nanomotors are very valuable. Your mitochondria are very valuable simply because they deplete deuterium for you. And for those reasons, you have to consider all these scenarios before you actually engage in any type of elite sports. They are all good, very important, I start every day with 30 push-ups. I walk my dogs every day. So I do exercise routinely, but it's comfortable. This is how much I feel comfortable with. I know it has a good strain on my body. It actually serves a better health, but I don't do extremes just because I have to challenge myself. I try to kind of find a middle way of finding a routine that is actually serving my mental and my physical health the best.
Gotcha. I have a random question before we dig into the deuterium depletion a bit more. Something I forgot to ask earlier, which is we talked about some of these pathways of elimination. So exhaling the water with deuterium, excreting it via the urine or via the fecal route. What about sweating? I'm curious, have you measured the content of deuterium in sweat, and is that higher than sort of normal? Meaning, is that a pathway of elimination for deuterium? So if someone goes in a sauna frequently, would that be helpful in depleting deuterium?
Indeed, yes, indeed. There's many ways of getting rid of deuterium. Sweating is one of saliva, lacrimation, body wax.
I don't think we want to cry our way to deuterium depletion. That doesn't sound like very
No, but
much
actually
fun.
through your nostrils, because it's connected your lacrimal, every gland of your body. It's not necessarily tears. It's actually more like vapor in your nostrils.
Okay.
That comes also from your lacrimal glands. Every gland of your body, including your skin and your saliva, and anyway you look in your body, the sebaceous and also the wax producing glands, they all get rid of deuterium one way or another. Usually your lowest deuterium is your breath, but your saliva, your urine, your fecal matter, and your sweat, they have higher deuterium, and they are all mechanisms of getting rid of deuterium from your body. You're right.
Got it. What about sunlight? I've heard that light and sunlight, and you alluded to this with photosynthesis earlier, but I'm also wondering about the capacity of light, whether it's UV light. I've heard some kind of mixed stories. Some people claiming it's the ultraviolet light, other people saying it's the red and near infrared wavelengths. The capacity of that light to interact with our cells and our mitochondria in a way that helps deuterium depletion.
That's right.
I've tried to look into this and I haven't been able to find a whole lot of research, but what's your take on this?
I sent you a good paper. It was written by a colleague of mine, Dr. Andrew Sommer. He is a physician, scientist in Germany. So he exposed cells to red light, low energy laser red beams, and actually he measured ATP synthase and ATP production in the presence of red light. And in fact, red light improves ATP synthesis by making water less viscous. Mm-hmm. So changing water's physical viscosity improves energy production, ATP synthesis, simply because more viscous water is able to move and participate in solvent and also in structural obligations per se in mitochondria. So you're right, when it comes to interfacial water, or the water that is in the mitochondria, which is interfacial water, more like surface water or structural water, light has a great effect, especially red light, because that's the most penetrating. Red light has a great effect on lowering viscosity, improving ATP synthesis and energy homeostasis.
But how does that specifically connect to deuterium?
Once deuterium makes water more heavy or makes it more viscous, if you expose your mitochondria to red light, it actually makes even semi-heavy water more viscous. So that water is able to move faster, leave the cells, or participate in the urea cycle. So after all, exposing your mitochondria to red light, especially, it actually makes more every kind of water that you can find in mitochondria more viscous. And if that's the case, then your mitochondrial nanomotors are able to function, rotate more efficiently. And this is what he found. If you actually increase red light exposure, then your water viscosity in your mitochondria, including the deuterium-loaded water, is decreased. So mitochondrial functions are increased and energy production is increased.
So got it. I think I know which paper you're referring to. I think I cited that in my book.
Andrew Sommer, and it just says red light water viscosity. Red light decreases water viscosity, improves ATP synthesis.
Right. So I'm familiar with that paper. So, but I guess my question is, where is that deuterium going, or what is the red light doing? That's like, where's if the water's getting thinner and more able to move easily, or these ATP motors are able to rotate more efficiently in the thinner water, the lighter water, where did the deuterium go to make that happen?
Yeah, so again, you have to kind of imagine mitochondria as water layers. You know, it's not really bulk water that flows around. It's actually one layer on top of the other layer. And when these layers move easier to each other, it's easier to move deuterium towards nitrogen, which is the urea cycle, meaning that you can actually mix this pool more efficiently. Even though it's surface water, you can actually get rid of deuterium by its more attraction towards nitrogen, which is the urea cycle's purpose. So you can faster exchange those layers, so they actually move faster. So your water dynamics in your mitochondria is much improved after red light exposure. So this constant deuterium filtering, constant deuterium binding urea cycles, they actually have more efficiency of removing heavy hydrogen-loaded, deuterium-loaded water, meaning that your deuterium your heavy or semi-heavy water is cleared from the mitochondria simply because the water core is more viscous.
Okay. So it's the water near the membranes is
That's
becoming
right.
thinner and
Thinner?
cleared of the
That's right.
deuterium.
That's right.
And so the deuterium is still sort of there in the cell, but it's being moved out of the area next to the membrane where the motors are. Is that correct?
Yeah, well, yes, indeed. You can actually bind heavy water to nitrogen, to urea itself, because urea takes them out. But for that, you have to move those layers. Urea does not pick up light water as efficiently as heavy water. So once those layers are moving because they are thinner, they are more viscous, then you actually get rid of more deuterium over a shorter period of time, meaning that it's just a more dynamic process after all.
Gotcha. Okay. So just a couple more questions here. And thank you for your time, by the way.
Of course.
So one layer is with mitochondrial health, there is some we know from lots and lots of lines of research that mitochondria are obviously extremely important in health and disease prevention. Obviously,
That's
energy, which is a big concern of people listening to this process. The way I conceptualize the story of chronic fatigue is very mitochondria centric, and I believe that's what the evidence points to. So mitochondria are really important. However, there aren't a lot of really good tests that we have to directly assess mitochondrial function. Now, I was doing an interview with someone recently, and he had just done a deuterium test on his body, and was really excited about it because he was basically thinking that measuring deuterium levels in your body is a really good proxy for assessing your mitochondrial health. So in other words, if you have low deuterium levels, that is a sign that you have highly functioning, healthy mitochondria. So my question is, first of all, do you think that's accurate to say that?
Yeah, that's a very fair statement. That's a very good assessment. Yes, that's right.
Okay. And then the second question is, I know there's a couple different methods of measuring deuterium. There's the breath, and I believe there's also the urine, and then I think there's also an MRI scan of your body.
That's right.
Do you have any thoughts on if all of those are valid, or if one wants to measure deuterium, is there one that's better than another?
So MRI or magnetic resonance is by definition is a proton spectra. So you actually resonate protons, and deuterium compromises the resonance. So actually, MRI is a straightforward deuterium measuring device, indirectly. Now, the Yale University Department of Radiology, they just started deuterium metabolic imaging, and that means they actually measure deuterium. They now obtain deuterium scans. And those are interchangeable. So practically proton or deuterium spectra in MRI image, by density, you can tell what's the cell's deuterium content in comparison with other tissues. So it's a good deuterium measuring device, indirect deuterium measuring device, MRI. So you can actually measure deuterium content, or at least have a look at deuterium content of tissues using MRI. It has a different view or a different analysis tool to measure deuterium in tissues using MRI, but it's very much possible.
Probably also very cost prohibitive for most people, I would imagine.
Yeah, I think after all, using a low magnetic field T1 sequence, that's probably your best bet. Using a 1.5 Tesla magnet. And using a T1 sequence, it's practically just how fast the protons return to their lattice, how fast the protons are able to return to their normal position once the radio frequencies turn off, and that depends on deuterium.
Right.
So because deuterium compromise.
So MRIs are probably the most accurate, it sounds like, but also probably the most costly and probably so expensive that they would be inaccessible for most people.
Well, it depends on how you approach this. It costs about $400 or $500, and you're right, it may be expensive. But since you can look at multiple organs in the same time, it may be also, if you are in general interested in your body's deuterium distribution, that probably it's cost effective. But if you are actually interested in just one particular tissue type, then it's probably expensive. You're right. It may be too expensive. Now, there are spectrophotometers. Say it again. But did you
I
have a
was just
question?
going to ask. So, there's these other methods of breath testing and urine testing. Do you feel that those are worthwhile, or is it one of these things where they're just not giving enough good data to be worth the money?
In health in general, you have to measure before you make any kind of assessment. Of course, they are very crucial because from those numbers, you know how your body is able to deplete deuterium. I give you a scenario. Your breath is actually coming from your metabolic water, at least some of it, because it's the venous circulation. The veins take the blood back to your lungs, and your lungs vapor is practically what you measure in your breath test. And usually the breath deuterium content tells you how efficiently your body is able to deplete deuterium compared to the environmental deuterium exposure. And if you compare this with your saliva and urine, and you see this window between your urine, saliva, and your breath, if those numbers are similar to each other, then you know your body, you're metabolically not very efficient of depleting deuterium. But if your saliva and your breath test shows a larger difference, then you know at least your body is able to produce more deuterium depleted water, and your deuterium depletion process to your metabolism is more efficient. So practically these three numbers, just like in any laboratory medicine, you measure simply just to know which way these parameters are moving, where you are at any given time, what is the environment exposure. You always have to do these measurements based on your original, and then when you imply a depletion method, how efficiently they work. You have to look at it's more like a one sample t-test, or like a I don't want to say self-experiment because we don't do human studies, but we don't do this for human study purposes. We do this for informational purposes, but that's practically what it is. At UCLA now we are carrying out preclinical experiments for example, in the Department of Pediatrics, where we actually look at the deuterium content of cells, look at deuterium exposure of cells, and we look at their cell death rate practically, and that practically just depending on the deuterium content of the environment. So the deuterium content of your body is a very important marker of where you are and in which way you should start depleting. The healthy deuterium content in breath would be probably below 130 ppm. We don't see this, unfortunately. We are overloaded of deuterium as a population because of food and many other reasons. Obviously, the environment and the global temperature changes, they all play a very significant role in this process. But once you actually start depleting, how efficiently you deplete and how fast you reach this biologically required range of 130 ppm, for that reason, you have to measure.
So just to be clear, the range is 130 to what?
We believe that anything below 130 in your breath is close to the desired range. Anything below 135 in your saliva and urine, because I told you those are higher than your breath samples. Those should be below 135. So you want to be on the safe side. It's probably below 125 when it comes to breath samples. That's what I like. And urine is probably below 130 or around 130, and urine and saliva. But practically those are the required numbers. We don't see those in the general population.
Now, how do you know those numbers are indicative of the amount of deuterium in the actual body? Meaning, is it possible that someone could have low levels in their body? Like if you did an MRI scan, you'd show low levels in the cells, in the tissues, but they're just very efficient at getting rid of deuterium so that higher levels are showing up in their saliva or urine. Is that a possible scenario or not so much?
Yeah, so these are surrogate markers. Whatever is in your breath, it's not the same as what's in your tissues. It's just practically a surrogate marker of what is your breath and usually what is your tissue. If your breath shows up at a certain level, what's the value of your tissues. Obviously, to start depleting or you see depletion, it's going to show up in your breath the first. So it's practically a surrogate marker of what your body's deuterium content is and what is your obviously, you have to measure a multiple of samples, and more desirable, it would be an MRI study, which shows you your tissue deuterium content. Since people don't have the money most of the time to do these type of tests, then we are actually, and it's more invasive, and it has to be medically indicated. So that's a more complicated situation. But actually, the measuring breath, saliva, and urine is the fastest, dirtiest, cheapest, I believe, and most informative surrogate.
And it is accurate and validated.
It's accurate enough. Let's put it this way. It's clinically not validated. Again, it's for informational purposes. I want to know what my deuterium level is. I can just breathe into a cold tube. You know, it's non-invasive. You can just do it wintertime in a cold window. You can collect your breath in many different ways. It's practically just, you have to have a cold water or you just need to condense your breath. So for informational purposes, it's an excellent method. Obviously, when it comes to clinical trials, which at UCLA we are pursuing very soon, and currently we're carrying out studies, but practically there are more accurate measurements. You're right. There's more accurate approaches, and clinically we will position it. This is actually the team stories when the biohacking is moving into mainstream evidence-based medicine. So we are now doing it the other way around. And this is my mission as a UCLA professor of pediatrics and a full faculty member of UCLA, after publishing over 100 papers in the medical literature and having an impact factor of whatever it is. It doesn't matter, but I'm a very accomplished academic scientist who has been doing this for a long time in the academic setting. And I'm a medicinal biochemist, so I don't do this just on, just like on my free time. So I have been studying these constraint models for a very long time, and we have published very influential papers. We just got cited by from Switzerland, from the Department of Pediatrics, and we wrote very important papers to explain how fatty acid, how deuterium-depleted water in various cell compartments should measure up after all for health and for curative purposes. But practically it's a surrogate marker. It's actually just an indicated marker of how much deuterium might be in your body. It's not an accurate measure, no way, but it's a good kind of look at it. And there's going to be much more clinically positioned laboratory tests for that, which will enter mainstream medicine. Currently, it's an integrative, alternative medical approach, and it's in the biohacking arena, but it's going to be evidence-based very soon, and it's making into academics medicine. Okay. How long it will take, I don't know yet, probably a few years, but we are carrying out those studies, definitely.
Okay, just a couple more things, and thank you again for your time. This is just fascinating, and I know there's more layers here that we need to cover. One that I want to make sure we cover, and feel free to treat this very briefly since we're sort of over time here, but deuterium depleted water, obviously, is you can buy water that is deuterium depleted water, low deuterium water, and drink it. And there are a number of studies now that have shown effectiveness of this kind of water in combating cancer development. I don't know if there's any on preventing cancer, but certainly in the context of people who already have cancer, they've shown that it can prevent the progression or metastasis, various beneficial endpoints. Can you briefly kind of summarize that literature?
Yeah, so there are blinded randomized clinical studies in prostate cancer that showed very efficient, very effective response to deuterium-depleted water, and deuterium-depleted water strength is in the 105-85 ppm range, I believe, based on the publications. There are about 8 to 10 publications that deal with clinical scenarios that relate to deuterium-depleted diets. We did publish about deuterium-depleted water in Neuro-Oncology, which is a very influential letter responding to a clinical study, experimental scenarios, and experimental animal studies that actually address the ketogenic diet. Those are in the medical literature. And there are actually papers that have been written from the mechanism point of view, mitochondrial papers, which we published with Johns Hopkins University. And there are currently studies that we are carrying out with promising results in neonate settings and to prevent acute respiratory distress syndrome, ARDS. And we have been able to address clinical problems based on deuterium depletion. Those are available in the medical literature. So if you type in deuterium depleted water or deuterium depletion, then you can pull those papers. If you type in Dr. Gabor Somjai, who actually carries out most of these, published most of these clinical studies, then you're going to find at least 8 to 10 papers, case reports, and also blinded randomized clinical study which show the benefits of deuterium depleted water. Takes a little bit of literature search, but you can find those papers.
Great. And then what about in the context of chronic fatigue? Has there been any research done linking deuterium to
yeah, I can't talk about
fatigue?
in detail, but we just reported to the California medical boards. They took the deuterium depleting argument favorably. So the highest medical regulating authorities now know about deuterium depletion and how efficient it is, especially in chronic fatigue. I can't talk about those in details. Hopefully soon we were able to do that. Practically, this is a little bit of time which are lagging right now just to wait for those clinical evidence to come out. But everything points to the direction of eventually this is going to make it into mainstream evidence-based medicine.
Gotcha. Obviously, deuterium depleted water is quite expensive. I'm wondering, do you think on a, outside of the context of somebody who already has, let's say, cancer, where we know that there's these trials, as you mentioned, that show benefits, what about like once a year for a month, every year someone does, drinks only deuterium depleted water for that month on a preventive basis? Do you think something like that would have any benefits, or would you need to be drinking it all the time for it to really
So
work?
they recommend it 3 times a year. So it's a cure, kind of it's not a cure, like it's a, how can I say, it's like 3 times a year for a certain period of time, which is a month. You can drink either 125. Again, I'm not involved in marketing. I'm not involved in pricing. I'm not involved in processing. I'm not involved in the market. I'm the scientist guy. So unfortunately, I can't really address that question, from the business point of view. Yet there are 3 kind of, we recommend, or Gabor Somjai recommends, that if you want to deplete deuterium through water, I don't recommend water, I recommend natural ketogenic diet. So I don't drink deuterium depleted water, I actually drink olive oil, or I don't drink deuterium depleted water, I actually eat raw pork fat, practically just bacon. So I'm not the water guy, I'm actually the water and the diet guy. So I don't think it's very feasible to drink deuterium depleted water. I think you should eat fat more and drink less water. Actually, you should not drink water.
Okay. So why don't you think it's feasible? Just because of the expense?
Because it's too expensive for depleting deuterium. You can do it much easier, much simpler, and much cheaper if you eat a natural ketogenic diet.
Okay. And the last thing you said, I kind of cut you off, but you were saying that you don't think people should drink much water in general, or specifically deuterium depleted?
Yeah, so you should drink. I believe that drinking is practically just as regulated as urination. You should drink when you're thirsty. You should drink just as much as you can kill your thirst with. You should actually be very careful how much antidiuretic hormone you have. With excess water, you can actually compress or suppress antidiuretic hormone synthesis, which actually helps your nanomotors and mitochondrial functions. So I actually stay away from water simply because I make my own water. I eat and drink enough fat to actually accomplish that. so I don't need water. It's a time-saving and it's a money-saving option. And again, if you need deuterium-depleted water, then you probably want to do it as a cure, like a certain period of like 3 times a year. And you don't have to drink a whole lot of water. You have to drink it with moderation when your thirst requires it, and then it's going to be less expensive. You don't have to drink deuterium water like you drink bottled water, because bottled water, you practically just drink 2 liters unnecessarily, in my opinion. But bottled water is practically just something you waste because you drink it, then you pee it out. So there's no sense to it.
Mm-hmm.
But if you do this with deuterium-depleted water, yes, indeed, it's very expensive. So that's why I usually recommend just actually eating fat and producing your own water.
Okay. As far as water sources, I know you mentioned at the beginning, it sounded like rainwater would have less deuterium content.
That's right.
I'm curious also about things like glacial water or spring water from mountains. Would those also have lower deuterium?
These are somewhat lower. These are maybe, if you compare them with the 150 ppm of your tap water, it's probably 143 ppm. I think the lowest as potable water we measured around 139, 140. That was the lowest. So they are in that range depending on where they originate from. More glaciary, more high altitude, more fractionated, more deuterium depleted. Then it's somewhat better, but you want to be in the 125 range. So rainwater is especially if it's several times fractionated. In natural scenarios, you can go down to 140, but if you want to actually go deeper or lower in deuterium depletion, then you have to eat low deuterium food, which will make you low deuterium water in your body, and that case, you can probably hit the 130, 125, below 120 range, which I believe is the desired biologically relevant range.
Gotcha. Last question. Again, thank you so much for going overtime here. This is much longer than I anticipated, but it's just a fascinating discussion. I have so many questions. I want to keep you here for 3 hours. But last question. You've obviously mentioned ketogenic diets, fats being lower in deuterium content.
Natural ketogenic diets, so grass-fed animals.
Okay. I'm wondering, there are obviously a lot of carbohydrate-containing foods, for example, berries, for example, lentils, that are decidedly associated with health benefits and
Mm-hmm.
Disease prevention benefits, and are associated with longer life and so on.
Mm-hmm.
I'm just wondering how you square that with the recommendation. I mean, obviously, we can certainly agree to avoid things like wheat flours and added sugars and refined carbohydrate products, and no one would debate that. But is there really an argument to exclude things like berries just because they're higher in deuterium content?
Well, actually, they're natural. What the species, the plants that you mentioned, they actually produce sugar, which is very interesting. Lentils, for example, or beans, for example, they produce actually sugar, which is actually deuterium depleted. There's a great paper about it, that actually there are some plant sugar sources that actually not only depleted, but they are depleted on specific carbons that are getting oxidized in our system. So it seems that nature figured it out. Not every sugar source is bad. It's actually the fruits, the like high photon pressure, summer, early fall type of fruits that are highest in sugar and deuterium. But actually, if you look at lentils or beans or some other plant products,
I would love to get that link with you and see what the breakdown of.
I can send you the paper, definitely. If you actually look at our medical hypothesis paper, the water exchange reactions, actually we released those papers, which are actually deuterium depleted sugars. So some foods, some plants are very healthy, especially because of their low deuterium sugar and their high phytochemical fat content. So those are just fine to eat.
Okay, and things obviously fat-rich plants. So I'm guessing things like avocados and nuts and flax seeds and things like that would be very low in deuterium.
You're right on. Yeah.
Okay.
That's right.
Excellent. Dr. Boros, this has been absolutely fascinating. Maybe you win the prize for the most fascinating subject matter I've ever covered on this podcast. I'm really excited to see this whole field of deuterium and disease and health evolve. I think it's fascinating. I need to get a couple papers from you. We're going to share them on this podcast page. It'll be at theenergyblueprint.com/deuterium for people listening, and you might have to Google how to spell that, but it's DEUTERIUM. Again, Dr. Boros, thank you so much. Is there any place that people can follow your work, or do you have anything you want to direct people to?
My website is Laszlo G. Boros, just my full name without spaces or dots, www.laszlogboros.com. And you can find all information as far as deuteronomics and depletion. Now we use depletion if it's deuterium depletion, so it's a DEUP. And the rest of the depletion word. But practically, I'll send you those papers. You can go to my website. I'll send you that information to complete this podcast. It's very honoring. If you have questions, just email me. And
Thank you so much.
This information to help your audience.
Yeah, this was an absolute pleasure. Do you have in your lab? Do you do any sort of deuterium testing? Do you want to let people know about that if that's something you do?
We don't do currently at UCLA deuterium testing. There are various ways of testing deuterium. There are reference laboratories in the United States where you can actually have your deuterium tested of water or any type of sample you might have. You just make arrangements with them.
Okay. And if somebody does want to test it, you would recommend saliva, breath, and urine to get all three measurements?
I would recommend you do breath, definitely, saliva, so it doesn't have to be three samples.
Okay.
Breath, saliva, or urine. I think that's the most useful scenario.
Okay, beautiful. Dr. Boros, thank you again. It was really an honor to have you on and fascinating stuff. Thank you so much.
Thank you. Have a good evening.
Hey there, this is Ari again. One more quick thing before you go. Just make sure to subscribe to our YouTube channel, The Energy Blueprint, and also make sure to subscribe to this podcast on your favorite podcast platform, whether that's iTunes or Stitcher or anything else. I hope you guys enjoyed this interview, and I will see you again next week.